Good morning, class. This coffee is good. Okay, up there's the motion detector. The motion detector emits and receives ultrasonic sound waves. Okay, the computer automatically graphs position and velocity versus time. The graph can be analyzed. You can do linear fits, quadratic fits. From the fit information, you can determine such things as original velocity and acceleration due to gravity. Ow! Oh no! Any questions? See me. Boy, could I use another cup of coffee. Or two. Good morning, gang. Today we're going to determine the acceleration due to gravity by analyzing a video. Get back here, ball, of a toss ball. Okay, here's the ball's vertical motion equation. In words, this equation states that the vertical displacement of the ball is equal to the original velocity times the time plus 1/2 the acceleration due to gravity times the time squared. Whoops, okay, so let's videotape the ball's motion. For a scale, I'm going to place two safety cones 1 meter apart. Good. Toss. Let's use Logger Pro and the video to determine G. First, import the movie to Logger Pro. Scale, 1 meter, locate origin, collect the position of the ball as a function of time. The horizontal and vertical positions as a function of time are automatically graphed. Next, do a curve fit. Use the curve fit to determine the acceleration due to gravity. Good morning, class.
Good morning, Mr. Wetherhold.
Today I'm going to tell you a story of how I acquired this creature for the biology department. Turn off the lights, turn on the projector. My adventure began in New York City. From there, I flew south to the jungles of the Amazon. This story is really interesting and appropriate because I had to use physics, as you'll soon learn, to capture the creature. Now, the flight was long and somewhat boring. When I finally got to the Amazon, I rented a vehicle and I drove for several hours. The natives told me that the creature I was seeking would be less aggressive if I offered it food. So I decided to hunt for something to give the creature. I soon spotted what looked like a red squirrel. I aimed above it to compensate for gravity. Physics is helpful. Finally, I spotted the creature. This time I must aim directly at the creature, since it releases its grip when it hears the noise of the gun. I successfully captured the creature, and now I can go home. Okay, turn the lights on. Let's talk about the physics. Without gravity, I would just have to aim directly at the creature to hit it. But there is gravity, and since the creature falls when it hears the gunshot, I once again aim directly at it. Bullet and creature fall together.
Mr. Wetherhold,
Oh my, the creature's loose. Everyone get out of here. Oh no, oh no. Whoa. Class dismissed. Well, hello, little man. So you're going to help me teach about man-made satellites. First, toss the ball. Good. Now draw an Earth and label it. Okay, we're going to use that later. But now I want you to throw the ball again. Put it into free fall. Notice that it has a curved path. Now I want you to throw it faster, and you'll notice that the curvature of its path is starting to match that of the Earth. So let's take this a step further. Throw the ball still faster, and notice that its curvature is getting closer and closer to taking it around the Earth. Still faster. Look at that. Okay. Now throw it at 8,000 meters per second, and it will circle the Earth. Watch out! Oh boy. Imagine that you're riding in this toy train. Relative to the train, the classroom is moving. Okay. Here's a video I made to illustrate that certain reference frames can give you strange illusions of motion. Here's my train. In a moment, I'm going to board the subway train. See you inside the train. Okay, here we are in the subway, moving along the tracks, approaching the next station where we're going to stop. Another train arrives at the station. Now our train begins pulling out of the station. Hold on. Haha, it was the other train that pulled out of the station. Now we're moving. Now we're moving alongside another train. Looks like we're at rest. Figuratively speaking, Galileo's still alive. Watch it.
That man's at the window.
Huh? Why don't you do a Galilean transformation? Ha ha! Morning. Consider a coffee mug on a table in an airplane accelerating to the left. If the mug stays on the table, friction must act to the left. If there isn't friction, the mug will slide to the right, relative to the plane. But remember, the plane and tray are accelerating. Therefore, the tray is a non-inertial reference frame. No. In this frame, a fictitious force would be introduced. On the ground, an inertial reference frame, an observer would simply say that the mug continues traveling at the velocity the plane had before the plane accelerated.
Let's now watch a movie of me riding in an airplane. Lights, turn on projector. Putting myself in a non-inertial reference frame, it appears as if everything's being pushed toward me. Putting ourselves in an inertial reference frame, we realize that there isn't enough friction to keep the mug and apple accelerating with the plane. When the plane is accelerating, it's easier to do the physics from the ground, an inertial reference frame. Boy, does this apple look good. Cool. Now the plane's an inertial reference frame, so the horizontal velocity of the apple is always that of the plane. Plane's traveling at a constant velocity. I drop the mug and it falls straight down, just like in the classroom. Both are an inertial reference frame, so the laws of physics hold.
Physics is fun. Well, that was great. Okay, so for homework, do...
See ya, Mr. Wetherhold.
Good morning, class. Let's talk about relative motion. Let's take a look at a video I made of me riding in a train. The train is traveling at a constant velocity. And I'm at rest relative to the train. So my velocity relative to the ground is the same as the train's velocity relative to the ground. Boy, this coffee is good. Suppose I start walking in the train. My velocity relative to the ground would be equal to my velocity relative to the train plus the train's velocity relative to the ground. If I walk to the left, my velocity relative to the ground is greater than the train's velocity relative to the ground. If I walk to the right, my velocity relative to the ground is less than the train's velocity relative to the ground. The equation I wrote is called the Galilean transformation. If I accelerate, my acceleration relative to the ground is equal to my acceleration relative to the train. While I'm accelerating, I'm going to be using an accelerometer. Take a look at this. Right now, I'm not accelerating. Liquid is level. Now, I'm going to accelerate to the left. And my acceleration relative to the train is the same as my acceleration relative to the ground. Now I'm accelerating to the right. And ditto. Okay, class, that's it for today. See you next time. Hello, I'd like to introduce a new cartoon character that was drawn by one of my students. His name is Little Man, and he's going to be starring in a new series called Little Man Teaches Physics. I hope you enjoy the first episode. Well, hello, Little Man. So it looks like you're going to teach us about Newton's second law. Acceleration equals net force divided by the mass. Very good, little man. Now, increase the mass. And what happens to the acceleration? Right, it goes down. Now, decrease the mass. There you go. What happens to the acceleration? Good, goes up. Now, increase the force. The net force, right. That's right, increases the acceleration. Decrease the net force. Very good, little man. Excellent job. Good morning, class. Yum, good coffee. The liquid in this vessel points in the direction of the acceleration. And when there isn't any acceleration, it stays level. Notice when I spin, the acceleration is directed inward. What we have is a centripetal acceleration. And a physics teacher who feels dizzy. This always happens to me. Okay, now I feel better. So, when a body travels on a curved path, it has a centripetal acceleration given by the speed squared over the radius of curvature. Let's watch a video of me driving a car. Okay, here we go. Keep your eye on the liquid accelerometer. Whoa. Whoa. Yikes. Whoa. The green liquid points in the direction of the car's acceleration. Okay, does anyone know what causes the car to undergo this centripetal acceleration? Good morning, class. Yum, good coffee. The liquid in this vessel points in the direction of the acceleration. And when there isn't any acceleration, it stays level. Notice when I spin, the acceleration is directed inward. What we have is a centripetal acceleration. And a physics teacher who feels dizzy. This always happens to me. Okay, now I feel better. So, when a body travels on a curved path, it has a centripetal acceleration given by the speed squared over the radius of curvature. Let's watch a video of me driving a car. Okay, here we go. Keep your eye on the liquid accelerometer. Whoa. Whoa. Yikes. Whoa. The green liquid points in the direction of the car's acceleration. Okay, does anyone know what causes the car to undergo this centripetal acceleration? Good morning. Newton predicted that weight was proportional to the product of the masses and the inverse square of the distance between the masses. Ta-da! Given my mass and the Earth's, my weight varies inversely with the square of the distance between the masses. Okay, so now I'm going to test this equation. I'm going to climb up this ladder and see how my weight varies with the distance to the center of the Earth. Right now, I'm at a distance of 1 Earth radius above the surface of the Earth, and I feel about 1/4 my weight. Now I'm at about 2 Earth radii above the surface of the Earth, and I feel about 1/9
my weight. Don't actually try this, gang, because there's no air in space.
Imagine that a hole was dug from Bermuda to Australia. And imagine that a person jumps into the hole in Bermuda.
Wyatt!
What would happen? Well, the person would fall. And while the person's falling, of course, the person would feel weightless. The person's speed would increase to a maximum value, which would occur at the center of the earth. There, the net force on the person would be zero. The person would no longer be accelerating, traveling at a maximum speed, however. As soon as the person leaves the center of the earth, as they're falling through the tunnel, their speed would start to decrease because now there's a net force acting the opposite way on them. By the time they get to Australia, the person would be at rest, and then the process would be repeated. The type of motion that the person is undergoing in this fictitious scenario is called simple harmonic motion. Now what I'm going to do is I'm now going to go to Bermuda, and you're going to go along with me, and I am going to jump into a hole that was actually just recently dug between Bermuda and Australia. Hello, I'm in Bermuda. It's great here. The weather is perfect. Now behind me you see the hole that was dug straight down through the earth to Australia, Perth, Australia. And in a moment, I'm going to walk over there, and on the count of 3, I'm going to jump into the hole, and let's see what happens. 1, 2, 3.
I'm falling, and I definitely feel weightless. I also sense that I'm going faster and faster. Now I sense that I'm going slower and slower and slower, but I still feel weightless.
Welcome to Perth. Hello.
Here we go again. Good morning, class. Morning, Mr. Wetherhold. On some coasters, you feel really light going down the first hill. The curvature of the hill is a free fall curve. Sometimes you feel light even on the second hill. That's because the curvature of this hill is also a free fall curve. Okay, let's watch this movie of me riding a coaster. The first hill that you see me coast down is a free fall curve, so I feel really light or practically weightless. The next hill the coaster negotiates is a free fall curve, so again I felt practically weightless. Riding coasters is a lot of fun because there's a lot of physics involved. Since those hills are free fall curves, you could literally remove the tracks and still enjoy the ride. Watch this. Okay, so I arranged to have the track removed. I'm in free fall, following a free fall curve. I'm in free fall again, following a free fall curve. By the way, these free fall curves are parabolic in shape. Okay, class, that's about it. Whoa, those darn apples. Oh. I think I'm gonna go to the local amusement park. Potential energy plus kinetic energy gives us the total mechanical energy. Take a look at this. Come on.
No. The potential energy plus the kinetic energy of the roller coaster is a constant. Assuming no friction, potential energy is converted into kinetic energy. Okay. Watch out!
And I get to talk.
Well, hello, little man. So today you're going to teach about a simple harmonic oscillator.
Equilibrium.
Its rest position.
This is its period of oscillation. Its period is equal to 2 times pi times the square root of its mass divided by the spring constant. And the reciprocal of the period gives the oscillator's natural frequency. Now let's take a look at a practical application.
In a lifetime, billions of waves wash upon the shore, delivering energy from far out at sea, without any material object making the journey. Leonardo da Vinci said of water waves, "It often happens that the wave flees the place of its creation, while the water does not."
All right, let's get down to business. I need a volunteer. Okay, Phoebus. What we have here is a single transverse wave traveling back and forth between us, delivering energy. The energy comes from us, but is carried by the wave. Waves on the strings of instruments are transverse waves. Whoops! Sound waves, the ones I'm creating as I speak, are longitudinal, a topic of a future class. Okay, how do you find speed? We learned this before. Phoebus.
Distance
Good.
divided by time.
Right. Okay, so now let's apply this to the speed of a wave. Let's start with a clean board. Oh yeah, I forgot to mention the other way to transfer energy. Particle transfer. Okay, the speed, Phoebus.
Is the TV broken?
Of course. Here's a sketch of a transverse wave traveling to the right. The length of the wave is called the wavelength. The speed of the wave is equal to the wavelength, or distance, divided by the time it takes the wave to travel this distance. Period. I love trains. Cool. Today's lesson, longitudinal waves. I need a volunteer. Virgil. Okay, take this end of the spring. Okay, so now I'm going to send energy to you, Virgil. See? See how the coils themselves don't move from me to you? Look at that! Yeah. Yikes! Whoa! Okay, class. To create sound, a longitudinal wave must have a mechanical, vibration. What else is needed? Phoebus, go ahead, give your answer.
An elastic medium.
Right. Let me just erase this. Question. If a tree fell in a forest and no one was there to hear it, would there be sound? Virgil!
Yes.
Okay, let's watch this. Sound needs an elastic medium and a mechanical vibration. I need a volunteer. Virgil. Sound requires a source of vibration and Phoebus.
An elastic
Very
medium.
good. Elastic. Now for a demonstration. The physics demonstration room. Okay, Virgil, I'd like you to come with me down into the physics demonstration room. Follow me. Okay, Virgil, I'd like you to go over there and get inside the vacuum chamber. Now I'm gonna seal the chamber from the outside world. All right, Virgil, would you please sing so I can test my oscilloscope? That's it. That's it. Very good. Next, I would like you to take a very deep breath and sing a single note for a very long time. And now I would like Roxy to turn on the vacuum pump, which will remove the air from the chamber. Note that you can no longer hear Virgil's voice. That's because there's no elastic medium. Roxy, turn off the pump. The elastic medium is back and we can hear Virgil again. Okay, Virgil, you can stop. I just demonstrated to you that sound cannot exist in a
Mr.
vacuum.
W. Roxy turned on the vacuum pump again. Help!
Good morning, class. My assistant, Karina, will help us with today's lesson.
Okay.
Today, we're going to learn about the Faraday cage. Let's charge Karina up.
Negative charge is transferred from the Van der Graaf generator's dome to Karina's hair, and to my hair and Albert's. Grounding leaks excess charge off. Thank you, Karina. You may take your seat.
You're welcome.
Okay, let me take care of Albert. Now, consider a charge conductor. The charge distributes itself uniformly along the surface in such a way so that there's no electric field inside the charge conductor. Place a positive test charge inside the conductor and it will experience a net force equal to 0. A conductor used to shield what's inside it from external electric fields is called a Faraday cage. Here's one. Step inside, Karina. Electric generator on.
My hair feels normal.
No electric field. And now, a special video. Like Faraday.
Where are Faraday cages in our everyday life? James? Like Airplanes are Faraday cages. They protect us from lightning strikes.
Listen to this.
Do you know why you're safe in a car when it's lightning? Because it's a Faraday cage. Next time you're in a lightning storm, go inside a Faraday cage.
That's it, folks. See you tomorrow. Good morning. Today we're going to study the electric circuit. Here's a simple one. It consists of a battery, 2 light bulbs, and a switch. A voltmeter and an ammeter read the voltage and the current respectively. A schematic diagram of the circuit looks like this: resistance, or light bulbs, and the ammeter. The voltmeter measures the voltage drop across the circuit. Open the switch, the lights go off. This is the voltmeter. It measures the amount of energy lost by charge going through the circuit. The current, measured by the ammeter, has one path to follow. Let's learn about how the voltage, current, and resistance relate.
I'd like to talk about my law, Ohm's law. The voltage across a resistor is equal to the current through the resistor times the resistance. There's 2 other ways of writing this. It's just algebra, though. It's not 3 laws, there's only 1. See? Okay, suppose voltage is held constant and we plot current versus resistance. What the graph would look like? Remember, voltage is constant. So current plotted against resistance would be inverse.
Thank you for the great presentation, Mr. Ohms. Mr. Ohms, I have a copy of your book. Would you mind signing it? Today you were introduced to the electric circuit, the series circuit, and Ohm's law. The world is full of electric circuits. Think of all the electric circuits in a typical city. Good morning, class. Today we're going to study the series circuit, in which there's only one electric current path, and the voltage drops across the resistances add up to the total voltage drop. Here's a schematic diagram of a series circuit. The zigzags represent the light bulbs. Does anybody know why the voltage provided by the battery is equal to the sum of the voltage drops across the resistances? Anyone? Yes? Yes, Daisy.
Energy conservation.
Very good. Let's continue this study by looking at this video. Mr. Ohms.
Thank you. Today I'd like to talk about the series circuit. There's one path for the electric
Mr. Ohms,
current.
would you like a cup
I
of coffee?
do not like to be interrupted. The voltage provided by the batteries is equal to the sum of the voltages across the resistance. Conservation of energy. Now, applying my law, we get, since the current throughout is the same, It gets kicked out of town. Notice that the effective resistance is equal to the sum of the resistances in a series circuit.
Thank you, Mr. Ohm. Next up, parallel circuits. I still can't believe you were almost electrocuted.
I actually enjoyed it. It cleared my thoughts.
Good morning, class. Today we're going to study the parallel circuit. After class, Mr. Ohm will be offering his book. You can see how the voltage drop across the individual bulbs is the same. That's regardless of the resistance of the bulbs, of course. Now we're going to watch a movie that Mr. Ohm made about the parallel circuit. Hooray!
Yippee! Hello.
Here's
My name is
Mr.
Mr.
Ohm.
Ohm.
Yes.
Today we're going to study the parallel circuit. Here's a schematic diagram.
This was filmed PES,
There's a voltage
pre-electric shock.
across the voltage source, V. There's a voltage drop across this resistance and a...
Coffee, Mr. Ohm?
No, I'm not interested. Please don't interrupt me again. And voltage drop here. The total current separates into I1 and I2. Now, I is equal to I1 plus I2. Using my law, we get this. From conservation of energy, voltages are equal. We end up with an expression for the effective resistance, which indicates that the more resistance is in parallel, the lower the resistance.
Wow. Thanks, Mr. Ohm. What's interesting about a parallel circuit is that, a bulb can be removed without affecting the other. When a bulb is removed, the resistance goes up. Let's review. In series circuits, the effective resistance is the sum of the resistances. Parallel circuits.
That's the equation.
No kidding. Okay, time to sell your book.
Miles high, standing by for the onboard engine countdown now. Altitude's 2
We have a
miles.
liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Tower clear. We got a roll program. Downrange. 3 miles high. Standing by for the outboard engine cut down now. Altitude's 2 miles. It is right on the top.
Oh, well, in Houston, you're good at 1 minute.
And ignition.